to know how to enhance pairing. So, Dror, can you?
Well, I have to start with ASA, of course. And, well, you've heard different views of ASA, and for me, ASA is the multi-talented physicist, and I have the pictures to prove it. We know that he's been a tank commander, that's seen behind the binoculars. When he was a student at the Hebrew University, he served as a radio operator on a merchant ship. That's true, that's what he told me. He surfs the waves, he runs marathons, and he's just a great guy. That you all know. What I can tell you from my own personal experience is that these nice traits of ASA have rubbed off onto his children. At least Omer, who is a student at the Hebrew University, and I had the good fortune to interact with. So many more happy and healthy years. So the work I'm going to describe today is basically an outcome of us nagging me for a long time to take a closer look at core as a method to investigate strongly correlated fermionic system, and a question that was implanted in my head by another very influential person in my life, Steve, about the role of inhomogeneities in superconductivity, especially superconductivity that is driven by strongly repulsive interactions. So that's what I'm going to tell you about today. And the work was done by two of my former students, Shirley Baruch and Gil Bacher. You all know that by now it's pretty clear that the cuprates show various signs of nanostructure in the underdog side of the phase diagram. That's under consensus. What is not is the question is, are these structures essentially in any important way for the understanding of superconductivity in these materials and in general? There is no consensus on that question. I will start by the minority view that says that they might be important and beneficial for superconductivity. And I think the main argument comes of this group of thought comes from numerical simulations of models like the Hubbard and TJ models on geometrically confined structures like these letters, where different signatures of pairing, such as the spin gap, show a large value on the confined geometries, and they tend to decrease when you extend the one-dimensional, quasi-one-dimensional system towards the two-dimensional uniform limit. Obviously, if you go to the very extreme inhomogeneous limit, say, of weakly connected Hubbard letters, you impair the propagation of holes through the system, and thereby you decrease the phase coherence, the other necessary component to achieve superconductivity, and that's bad for TC. And the best experimental example that I know of is found in LBCO, where the maximal single particle gap is found exactly where TC drops to 0, around 1/8, where we know the system develops very robust and static long-range charge orbit. The majority of the community would tell you that these structures are inessential. They might be important, but they are not the important ingredient for superconductivity. And let me mention two of the other school of thoughts that might have something to do with the role of inhomogeneity. And the first one is due to Anderson, that proposed this RVB state as a guess for the state of the undoped system. It was his suggestion was for a spin liquid, this is not completely disjoint from what I was telling you before, because we know that the two-leg ladder has a wave function which is pretty well described by such a wave function. However, we know it was found very quickly that this state is very delicate. And in most cases, except for very, very special cases, it's unstable towards various ordered states such as antiferromagnetism and various valence bond states. An example is shown here. The other approach involved again magnetic excitations as a source for pairing in the Hubbard model and in the cuprates, and it's based on the proximity to the antiferromagnetism in the Mott insulator. And we know that one cannot use the large magnetic susceptibility of the fully ordered state, namely the Goldstone bosons. This is an argument due to Schrieffer that showed that the electron-magnum coupling vanishes exactly where the susceptibility diverges. But the hope was, or is, that once you couple these excitations to the fermions, they become overdamped, local. These arguments by Schrieffer don't hold anymore, and maybe this is the bosonic glue that glues fermions together. So the work tries to tie somehow these different school of thoughts and answer, are they related in any way, or is inhomogeneity play a role in the balance between the different mechanisms that I just described? And on the technical level, I wanted to find out whether core is a good numerical method to study fermionic systems, and I'll show you the results. So the model that we decided to study, at least initially, is the checkerboard Hubbard model. It's just the Hubbard model which is comprised of plaquettes with hopping between the sides on the plaquette and an on-site interaction U. And different plaquettes are connected by a different hopping amplitude T prime. This model was studied extensively by Steve and collaborators, and Steve already showed the complicated phase diagram that arises when one studies the model in the low or the small T prime limit. I'm not going to discuss this at all. What was essential from our point of view is the fact that Steve and his group diagonalized the 2x2 plaquette system exactly. So this served as a benchmark for our core calculation. So Sylvian, he told you something about core yesterday. Let me recap very quickly in the following two slides. What is core? So core is a real space RG scheme to obtain low energy effective Hamiltonians. And it works like that. The zeroth step is to break your system into elementary blocks. In our case, the elementary block is obvious, the plaquette. The next stage is to diagonalize each of the blocks exactly and keep m low-lying states out of the low energy spectrum. This should be driven by some physical intuition. There are no rules for picking up the important states. These states, these m-kept states, define for you an effective Hilbert space for the rest of the calculation, which is just the product tensor states of the m-kept states. You may think about these m states as m types of hard core particles. You can have one on each plaquette. And the energies of these states on a plaquette define the on-site energies of these m types of particles. The second stage is to diagonalize the two plaquette system and keep m squared states. Now you take the m squared low-lying states and project them onto the effective Hilbert space, the space of tensor product states of the m states that you kept on each plaquette. And the energies of these m squared states define for you effective interactions between these n particles on neighboring plaquettes. And you can carry this to the nth order, and you end up with an Hamiltonian for these n types of hardcore particles that now interact via n-body interactions that extend over to a maximal range of n. And now you have to do something with this Hamiltonian, and you can take various routes. We diagonalized it exactly. Okay, so which states should we keep in our problem? We're interested in the lightly doped system. So we have to keep the ground state, the half-filled ground state of the plaquette, which is has this nice property, which is that it's almost an RBB state. It's at least in the large U limit, it's just this pair of singlets minus this pair of singlets. Now we're interested in pairing, so we should keep the two-hole state, the ground state. And this is a boson with a D-wave symmetry on the plaquette, D-wave-like symmetry on the plaquette. We're interested in asking questions about pairing, so obviously we need to keep also single fermions. And there are 4 degenerate low-lying fermionic states on the plaquette, so we keep them as well. And we tried to do that at first, and it completely failed. It turned out that it's necessary to keep this first triplet of excited state of a single plaquette in order to get any sensible results out of the calculation. And these are 3 states with S equals 1. And this will play a role in tying together the various ideas that I was presenting before. So we have m equals 9 in our calculation, we have m different states, and we do the calculation up to range 2. That's the minimal thing that we could do. Okay, so here's the results for the pair binding energy on a plaquette. And it compares the core calculation with the exact diagonalization on a 2x2 cluster. So what is the pair binding energy? I give you 2 clusters and 2 holes, and I ask the question, whether is it better, energetically speaking, to put the 2 holes on a single cluster, or to break the pair and put 1 hole on each cluster? Okay?
This is 2x2 clusters of plaquettes, so this is 16 sites.
Correct. Yeah, the thing that is drawn up here.
Oh, yeah.
According to this, the definition that I take, if this quantity is positive, it signals a tendency towards pairing in the sense that you prefer, energetically speaking, to put the 2 holes on a single cluster rather than separating them and putting 1 on each. So you see that the qualitative behavior of the exact results, which are here, are captured by core. However, there are problems, and problems occur in the small u, large T prime limit, where core overestimates the pair binding energy. And this is basically due to the fact that in this limit, the correlation length grows, and you necessarily need to keep larger or longer range interactions than the range 2 interactions that we get. The other problem arises in the large U, small T prime limit here, in the corner here, where you see that core again overestimates the pair binding energy. And that's because in this case, core fails to capture the right ground state of the system. Nobody guarantees that the ground state of the system, for instance, would have a finite projection on the effective Hilbert space that you work in. And in that case, in that particular case, that's exactly what happens. And this is a signal that your choice of this m initial state that you keep is insufficient. Something else should be kept, the nature of the ground state has changed, and you should be aware and take care of it. Okay, but looking at various other quantities, I won't go into that. I would say that within the core approximation that we took, we are convinced that it gives at least a qualitative understanding or qualitative agreement with the exact diagonalization results, as long as you don't go too much towards the fully homogeneous limit or using very, very strong interactions. So based on this understanding, we set out to calculate larger clusters. And for example, these are the results of the 3x3 cluster, plaquette cluster. And we find very similar things in terms of a large maximum in the pair binding energy around U equals 6, and about T prime equals 0.5 or 0.6. This happened over or in all the clusters that we studied, which included various ladders, this cluster. And after our paper came out, there was another DMRG calculation of Steve Evans and collaborators that looked at this plaquette ladder and found basically the same thing, but on a much larger system. Let me point out that our results are not due to a single plaquette physics. Since the maximum here occurs for U equals 6, where the plaquette has no positive pair binding energy at all. It doesn't point to pair. So this is somehow due to inter-plaquette physics. And we have other indications that what we see is due to pairing, and this is one of them. This is the spin gap, the energy cost to excite the first S equals 1 excitations above the S equals 0 ground state. And you see that the two follow each other very closely, which means that the lowest S equals 1 excitation is indeed due to the dissociation of a whole pair here. You see that the spin gap starts to go down. It reaches the maximum before the pair binding energy, and that's an indication, we think, that a bound magnum whole pair exciton is formed. And there were others that, including Sylvian, that I think so similar things.
One second, you might hear a siren in the next few minutes, and it's just a drill. So.
Not true. Okay, so let me ask the question, how robust is this behavior? And we asked this question, and we decided to look at it by studying a deformed model. And the way we decided to deform our model, this checkerboard or plaquette model, was to add next nearest neighbor hopping, this TD. And this has two reasons. One, it's large in the cuprates, and more importantly, maybe, it's known that if you take a negative value for T, this TD that I defined here, you tend to decrease the the on-plaquette pair binding energy. So we were interested to see whether by killing the pair binding energy on a plaquette, we kill the effect on larger clusters. And we did both exact diagonalization and DMRG calculations. And here I show DMRG calculation of a long two-leg ladder. And what's seen here is that the effect persists. If you go to negative next nearest neighbor hopping, it persists, but it's no longer there if you go to large interaction and larger or higher values of the doping. So it exists, but in a narrower region in phase space. So the question is why? What's the underlying mechanism behind the enhancement? So core gives us a tool to try at least to give an answer or indicate a possible direction. So the effective core Hamiltonians that we calculate contains 45 different couplings. There is no sense in showing you 45 different couplings. So I grouped them into two groups. One that involves the kinetic energy, holes and pairs hopping from plaquette to plaquette, and the rest, which I call potential energy. And what I draw here is the kinetic energy, the sum of the kinetic energy terms, their expectation value in the ground state as function of T prime. And you see that everything is basically driven by kinetic energy up to the maximum of the pair binding energy, which is here about 0.6. And after that, nothing really happens. The kinetic energy saturates, and I don't really believe in the core results beyond this point. Yeah.
This is the ground state energy or the pair binding energy?
That's the ground state energy or the kinetic energy piece in the ground state energy. And this is the potential energy piece in the ground state energy of the 0, 1, and 2 hole ground states. So just by looking at it, you see that things are driven by kinetic energy below the maximum, and things are driven by potential energy above the maximum. So we took a closer look, and this is the kinetic energy terms again, the contribution to the ground state energy, and here in black, their contribution to the pair binding energy. Okay? And I divided them into two groups. One is bare fermion and pair hopping between plaquettes, and the other group is contains hopping that involves the antiferromagnetic magnons. And you see that while the bare fermion and the pair hopping contributes positively to the pair binding energy, this is this graph, the hopping processes involving the magnons always contributes negatively to the pair binding energy. Up to the maximum, things are determined by these processes. These tend to decrease the pair binding energy, but this is the dominant part. Beyond the maximum, you see that things change rapidly, and they more or less cancel each other. So the kinetic contribution to the pair binding energy practically saturates here. Okay? So the outcome or the bottom line is that the increase in the pair binding energy is due to a gain in kinetic energy coming from the hopping of pairs relative to fermions without involving any magnons. Beyond the maximums, things change, and the decrease in the pair binding energy is mainly due to the interactions of the fermions and the pairs with the antiferromagnetic magnons. Okay? Below the maximum, the pair binding energy, the direct interaction between the pairs and the interactions with the magnons, again, more or less cancel each other. And beyond that point, this dip is what causes the decrease in the pair binding energy. So just, again, by looking at it, you see that the magnetic background of the system plays an essential part in determining the pair binding properties of the system. So having understood that, we looked at the content of the ground state, and here I show the number of pairs, fermions, and magnons in the ground state of the system as a function of T prime, and I do it for a different number of holes. So you see that not much is happening in terms of the number of pairs and fermions, but the number of magnons increase quite rapidly around the value of T prime, which corresponds to the maximum of the pair binding energy. Moreover, we calculated the antiferromagnetic stagnant magnetization of the system, and again, it's practically flat up to the maximum and then starts to increase. So the message, at least from this particular set of calculations, is that we can correlate the maximum in the pair binding energy with a change in the magnetic nature of the background in which the hole popped. Okay? Below the maximum, its nature is RVB-like. Above the maximum, it turns into more antiferromagnetic, at least locally. So our suggestion is that the way inhomogeneity helps helps pairing is by suppressing the instability of the RVB state especially towards antiferromagnetism. That's a suggestion based on what we find. We don't have, The final thing we wanted to show or to ask is whether the inhomogeneity is beneficial for superconductivity. There is a difference between pairing and superconductivity, since for superconductivity you need to have phase coherence on top of pairing. And we set up to calculate the phase stiffness, and that's what's basically shown here as function of T prime. And we ran into various problems with core beyond this point. So I cannot extend, we couldn't extend these plots all the way to here. So with a loving eye, you would say that there is a maximum here also in TC, which is determined by, in that case, by the phase stiffness and not by the pairing, but it's kind of delicate. I'm not sure I can commit. I know that I cannot commit to a conclusion about that. So let me finish with the conclusions or summary. I think that I know that I showed you that there is a maximum or optimal value for inhomogeneity, at least in the form that we looked at, that exists in various variants of Hubbard models. We suggest that this maximum is due to the local stabilization of RVB-like correlations due to the inhomogeneities. There are various open questions. One that I just posed, is there an optimal homogeneity for superconductivity? Is this important for the couplings at all? I would tentatively say that I think that it is for a system like LBCO, where the charge order is so strong. I'm not certain that this is the case in the other materials where the charge modulations are very weak. And lastly, can it be used? Can we engineer a system that takes advantage of the enhanced pairing by creating such a nanostructure and in parallel taking care somehow on increasing the phase difference in the system, so to achieve a large TC? And again, we have some ideas, but nothing concrete yet. Thank you.
I wonder if your view of the positive interpretation, it seems to have almost going very critical point to how to be a technical measure.
Yeah, it might be, but we couldn't access or answer such a question. The small clusters that we had.
The T prime model does really has one critical point kind of.
Right, but most of what I showed you was not productive.
The view that the T prime less than T makes the range 2 more accurate, because that's essentially what we took.
Definitely.
And it would be very interesting to look at range 3 and 4 and see what they do when you take T prime to T, right? Which my estimate
Definitely. Definitely. After this project, we tried to implement for the Hubbard model on the triangular lattice. And there we did go to range 3. And things sometimes got better, sometimes didn't. So it's problem specific. I can't give you a general answer.
I have a question. Is there a chance to use this to calculate quantities like air temperature, TC, extend to finite temperature measurements that one can compare with experiments?
It's difficult.
Most important is air temperature.
I don't think so. It's the system. The method is geared towards zero temperature calculation. So you and that's what we did here. We calculate various quantities that are indicative of TC, such as the pair binding energy, the spin gap, the correlation, the superconducting correlation, and the superconducting stiffness. But we had to infer TC somehow by applying various criteria that for example, we associated this pair temperature with the pair binding energy based on just our understanding coming from BCS. We don't have a direct measurement of P in that case by actually calculating the system at finite temperature.
Okay, we have to move on, so let's thank Dror again.